So the problem is search a 2D matrix. So the idea is you're given a matrix and you want to just return true or false, depending on if the value you're searching for, the target, is in the matrix somewhere. Now, normally this would be an m by n, an O of m by n solution, right? Because you pretty much need to search the entire matrix. But you're given properties that make this a little bit easier in terms of efficiency. The integers in the row are sorted from left to right. So within each row, it's essentially a sorted array. And now what makes it even easier is the first integer of each row is greater than the last integer of the previous row. Essentially meaning throughout the entire array, going this way, it's sorted. If you were to take this thing and flatten it, so this row's first and then followed by this row, followed by this row, it would again just be a sorted array. So that makes it very easy to solve this problem. You know, if the rows could go anywhere they want, if this 10, 11, 16 could go up here, and then the 1 would be after that, it'd be a little bit harder. But because it's sorted, you pretty much just need to find a way to use binary search on a matrix, which is what I'm going to do. So the idea, we want to first check if I guess an easy, and this might not even be necessary, but an easy way to check if the number simply isn't in the array is if it's less than the first element. And that's what I did in my solution. I'm realizing now you could also check if it's greater than the last element, but it really doesn't matter. I'm actually wondering if I even need to do that check, period. But I suppose it's just a way to save some time in certain cases. But we'll do that check first. So if target is less than the first element, and just return false. And then we'll do a binary search, but we're doing a binary search on each row individually. So we'll say for each row in matrix. Now, when we're looking at a row, like say we're looking at this first row, we want to know, like if we're searching for 20, we don't need to do, because we know below we have a range of 10 to 20 down here, or let's say we're searching for 15, it really doesn't matter, but we're searching for a number that's not in the current row. We don't need to waste our time doing binary search on this row, just to make it a little bit more efficient. So what we'll do is we'll say, okay, if the number is less than or equal to the last element in the row. If it is, then we know, okay, if this number exists, it's going to be in this row somewhere, based on the constraints we have, or based on the properties. So we'll check for that. So we'll say if target, we'll actually check for the opposite case so we know when to continue. So if target is greater than the last element, row is the actual, the row of elements. If it's greater than the last element, we'll just continue on to the next row. So otherwise, we're assuming we're in the right area of the matrix at this point. So we'll just do a binary search. So we'll set the left to 0, the right to the length of the row, minus 1. And then we'll say while left is less than equal to right. And we'll grab our center. And then we'll check, is the target equal to the center? Is it less than the center? Is it greater than the center? And based on which one of those is true, we'll adjust right and left. So the target equals the guy at the center. And we'll just return true because we found our element. Otherwise, if target is less than the guy at the center, then we need to adjust right to be center minus 1. Because let's say we're searching for 4, and let's say our center is 5. 4 is less than 5, yes, so we'd move the right to be over here. So now we're searching in this range. Else, and this is target is greater than row center, let's say left equals center plus 1. So the opposite case, let's say we're searching for 4 and 3 is the center. Is 4 greater than 3? Yes. So we need to adjust the I believe left pointer to be over just a little bit. So now we're searching at the end of the array. And at the very end, if we went through all the rows, all the values, and didn't find it, we'll just return false. And this, I believe, this could technically be mitigated. No, I guess it couldn't be. I was going to say it could be mitigated by adding up here another check to see if it's greater than the last element, but that wouldn't take care of something like 32 that exists within the bounds of 1 and 60, but doesn't actually exist in the array. But I believe this should work. So this is a binary search in a matrix. I wonder, I haven't really looked at the time complexity. Space complexity should be constant. Time complexity for each row, so n, that's O of m, times log n, I guess. I wonder if there's a way to get log m times log n or something. I don't know. Hey, it works. I don't care. It works.